Thank you. Good afternoon, everyone. My name's Robin Morris. I'm convener of the Oxford Energy Network. This is the penultimate seminar for this year. Apologies for the postponement of last week's talk, which had to be postponed at short notice, but we're hoping to get Tim Stone to speak in Michaelmas term on his views on the prospects for nuclear power generation in the UK, which will be interesting. So to this afternoon, the many colours of hydrogen assigned to different methods of the production, perhaps intending using colours to convey some sense of the impact on the environment and so forth. And actually, a colleague of mine who's joined from Cambridge today, Andrew, first introduced me to the idea of a new colour of hydrogen that was something I'd not heard of before, gold hydrogen. So what's great to me is it doesn't involve that massive amount of energy that goes into breaking the covalent bonds that normally is involved in producing hydrogen. So we're really delighted to have Chris Ballentine join us, briefly at the University of Manchester, and Chair of Geochemistry and former Head of Department of Earth Sciences. So Chris, I previously would have associated with using isotopes to work out what's happening underground with lots of flows and movement and so forth of noble gases, those kind of unreactive things. So now we seem to have moved on to very reactive gas. And what I think is going to be really interesting is to understand, really, is there a prospect for gold hydrogen to make a significant difference in what we need to do in attaining a net zero or zero carbon energy system? So Chris, I'm going to pass over to you and make sure that you can move the slides. Thank you.
Great, thanks very much, Robin. As you say, there are many colours assigned to hydrogen. I'll talk about a few of those in a minute. But first of all, I want to acknowledge my collaborators, John Gallows from Durham and Barbara Sherwood Lollen. I'm not going to name them all. I've got a few in the audience today, but I'll just call it my rogues gallery, who do the. I'm presenting their work today, and I want to thank them very much for that. So there is an entire spectrum of colours assigned to hydrogen, and the hydrogen, as you may well realise, is not all equal or even. Mostly hydrogen today is produced by steam methane reforming, so you heat up methane with steam with a catalyst, high temperature, high pressure, and you break that down into hydrogen and waste products.
Chris, I'm very sorry to interrupt you. I failed to share your slides for people who are online, so let me just start the sharing. I'm very sorry.
Right.
Hopefully you can now see the slides.
Were they able to hear me?
Yes.
Great. I won't step back to the title slide then. So we have grey hydrogen, which today is the dominant source of man-made hydrogen through steam methane reforming, and it has a heavy carbon footprint. Blue hydrogen is exactly the same process, but that is with the CO2 extracted and buried. And green hydrogen, which utilises renewable resources, renewable power such as wind and solar to split water, generating hydrogen and oxygen. Both blue and green nominally have a much lower carbon footprint. So I'll be talking a little bit about grey, blue and green hydrogen, mostly for context. I've put in the corner the elephant in the room, which is our reliance on carbon. And I've put, just to give you some sense of scale, the market. If anybody wants to pin that market down, they're welcome to, with the current fluctuations in petrol prices. But what it does is place in perspective the amount of hydrogen that we're producing compared to the oil economy. And it's really tiny. We're looking at a small amount of the oil and gas economy with hydrogen today. And clearly, if we're to step this up and if we're to move to a net zero environment, then hydrogen is seen to play an increasingly important role in a broad spectrum of the energy mix. And the International Energy Authority released a roadmap to the global energy market called Net Zero by 2050. this gives one view on where hydrogen may play a role, but what you can see is this scale up from approximately 87 million tons of grey hydrogen to 540 million tons of green or blue hydrogen required in that particular model to meet the net zero energy mix by 2050. I'm not going to read the small print, but scaling up to do that is going to be a massive, massive effort. It requires a huge amount of resource, a huge amount of infrastructure, and that is stepped. Most of that has to happen before 2030, and one of the key components in achieving this is simply the cost of hydrogen per kilogram. If we're not capable of reducing the cost of the hydrogen that we generate through blue or green hydrogen, it's not going to be. It's not going to generate the impact that we need, and there'll be social resistance against that. Certainly, with the scaling up, green hydrogen is thought to come down to between 1 and I've seen numbers as low as 2.5, between 1 and 2.5 kilogram US dollars per kilogram of hydrogen. Blue, similarly, I've seen numbers lower than this is a KPMG estimate, between 1 and 2 kilograms US dollars per kilogram of hydrogen. But current cost of blue, current cost of green is not competitive, and that scaling, in addition to the infrastructure requirements, that cost also has to come down. One way of bringing that down is to look for other resources which are cheap. And natural hydrogen has come into focus recently. This is hydrogen produced in the ground by natural processes over geological time. And as a society, we've been aware of these gases for a long, long time. If we go to Chimera in Turkey, there are specific types of rock which react with water. They generate hydrogen. That hydrogen reacts and produces a bit of methane, but that hydrogen methane mix burns at the surface, and no doubt gave rise to the Chimera monster that breathes fire. More importantly, in Africa, very recently, back in 2015, a farmer drilling a well for water struck a gas. The gas flowed. The farmer unfortunately tested it with a match and is no longer with us. That gas turned out to be 95% hydrogen. It wasn't a single small occurrence. It is a major and significant pure hydrogen resource, which now has between 12 and 15 boreholes drilled into it and is producing. The data that comes out of Mali is limited. We don't have volume estimates, we don't have flow estimates, but it's certainly locally significant and potentially regionally significant if you listen to some of the company talks that are coming out. More importantly, when you're flowing this natural hydrogen, the cost of this natural hydrogen, by the time you've put in place the geological infrastructure, the geological understanding, the seismics, the visualization of the rock underground, the drills and the infrastructure to collect and clean and pipe it. Even with all of that in place, we are looking at a cost which is competitive and in fact more than competitive with blue or green hydrogen. Because this is coming out of the ground as pure hydrogen, there is almost no carbon impact or carbon footprint associated with that particular gas field. So hydrogen is derived from two sources. Hydrogen is a very slow reaction of water with a specific type of rock, an iron-rich rock. It's the hydration of that rock. It produces a nice green rock called serpentine, and it's called serpentinization by the geologists. But effectively, you're reacting water with iron, oxidizing the iron and generating liberating hydrogen. It's a very, very slow process in many parts of the crust. It's occurring on timescales where other processes, such as radiolysis, also become significant. So uranium and thorium occur in naturally small quantities in rock, variably distributed, but also in the iron-rich rocks. The uranium and thorium react with the same water. When I say react, I mean the radiation emitted by the uranium and thorium radiolyzes the water and splits it into hydrogen, into other products. And the hydrogen stabilizes and forms a significant source of hydrogen in the subsurface. Well, that's the source of hydrogen in the subsurface. It's that particular iron-rich rock. It's not a rare iron-rich rock. Iron-rich rocks, ferrous-rich, particular oxidation state, form 70% of the continental crust. A lot of it's still buried under sediments. A fair amount of it is exposed on the surface. But we have a vast amount of the continental crust. It's huge in volume, and we're not short of water either. Particularly like this graphic from the USGS. If we took all of the water in the oceans and put it into a little sphere, that's how much our oceans look like. Groundwater, that's water underground, forms this tiny little ball here. And if you're interested, surface water, the rivers, the lakes, form that tiny little droplet in the corner there. It's this stuff that's of interest. The fresh groundwater is water that we use for agriculture, for the big shallow aquifers. But beneath that yet, there is water occupying the rock pore space, which is more often than not saline, so it's not usable for farming or drinking water. But it's that water which is slowly reacting with the rock over huge volumes. It's very slow, but the volumes are large. And it's only recently that we've calculated the rate at which hydrogen is produced in the continental crust. It's produced dispersed throughout that entire mass, but the mass of the continental crust is so large that it matters. The amount of hydrogen generated is equivalent to the hydrogen generated by the oceans circulating around the mid-ocean ridges that form the oceanic plates. And interesting, 30% of the production is by radiolysis, and the remaining 70% is through that water rock chemical reaction. So we've got two advantages. We've got the volume. The rates of production are very slow, but the volume is huge. The age of the continental crust is also ancient. I think it's very easy to forget that when we talk about engineering timescales or burying of carbon dioxide, we're thinking of 10 or 20 or 30 years, or generational years, 100 years, 200 years, 1,000 years, when we're thinking of nuclear waste disposal. The continental crust on average is 2 billion years in age, and for 2 billion years, it has slowly been generating hydrogen. So the key question is how much and what's happened to it. And that's where I'm going to start, what I'm going to start talking. Well, let's just do a very, very trivial calculation, and I want to stress this is trivial. Now we know the rate at which the hydrogen is generated in the continental crust. Let's throw away 1 billion years. Let's think about how much hydrogen is generated in 1 billion years, the amount of hydrogen generated in 1 billion years, if we could collect it, and we can't, not all of it. If we could collect it, it would provide the amount of energy equivalent to society's use of all of the oil and all of the gas for the next 170,000 years. So we only need to find a small proportion of this naturally generated hydrogen, find regions where it might be concentrated, might be preserved, and might be accessible to make a difference. The question is, where are those places, and what criteria do we need to find it? We do see them. We do see hydrogen seeps globally. This is a very nice compilation by Vyacheslav Zagonik, 2019. You can see a lot of the data is from Russia. The Russians spent a long time collecting and were very interested in hydrogen sources. I think if we looked more deeply in Africa, South America, Australia, we would find a similar density, but What this looks like is very similar to the seeps of hydrocarbons that we would use as shows when we were first exploring for oil and gas. It's the first sign that hydrogen is preserved, has found a migration pathway and has reached the surface. In any exploration strategy, you'll be looking for deeper in that migration pathway where it might have accumulated in concentrations that are commercially accessible and usable. But we're not short of hydrogen seeps occurring at the surface in concentrations greater than 10%.
Rare.
So what we do need to understand, we need to start putting together the pieces that allow us to form an exploration strategy. There's no point in finding a seep, looking locally and drilling and hoping. Drills still cost a lot of money. We need to understand whether or not the hydrogen is preserved on geological timescales. There's no point in thinking that this is a wonderful new resource if the hydrogen is generated and chemically reacted or otherwise used and disappears. How is it released from this large volume of the continental crust? What are the mechanisms that can bring it to the surface, focus it, and put it into forms that are accessible to us? In other words, how does it come to the near surface, generate a gas phase, which then behaves in a similar way to oil and gas and might then be trapped and accessible? So we need to understand how it forms a gas phase. We need to understand, in particular for hydrogen, it's incredibly diffusive. And because we're looking at very, very long timescales, we also need to understand the types of rock that can prevent excessive diffusive loss through those rocks, because we're not looking at oil and gas. We've got to think longer timescale. So we need geological trapping structures which are impermeable, more impermeable than traditional trapping structures used for oil and gas. And we also have to understand how long it stays in those structures. We've made a lot of advances in understanding slowly generated, highly diffusive, highly mobile gases by looking at helium. Turns out that helium is really, really useful because helium is co-generated with hydrogen. So we can use our understanding of helium to start putting together how much we understand or need yet to understand about hydrogen migration and generation and preservation. So just to go through those components, both helium and hydrogen are produced by slow dispersed processes. They need to be released, they need to be transported, they both need to be focused, they both need to be trapped. One huge difference, and I'll come to that at the end of my talk, hydrogen is not conservative. Helium is chemically unreactive. So it's an indicator of the processes that have brought it to that place. And we can use it as an indicator of the system. But we also have to understand the environment and conservation of hydrogen and the environment that best preserves hydrogen as well as helium. But I'm just going to take a slight side and talk a little bit about helium because it does track hydrogen. Worldwide demand for helium is reached a critical point. It's hugely used in medical applications with MRI scanners, in rocketry, electronics and semiconductors. It's got irreplaceable physical properties, which mean that you cannot find another gas that has the same property. You cannot supercool magnets without helium. You cannot operate factories producing semiconductors without the cooling capability of helium. It was first found by accident. There was a well drilled in Dexter in Kansas in 1903. It burst to the surface, and unlike the poor farmer in Mali, the farmer in Texas tried to light this gas and it wouldn't light. It just blew out his torch. He threw it through burning bales into the gas stream, and it just extinguished the gas. It extinguished the flames, principally because this was dominated by nitrogen and helium. And very close by, they discovered one of the largest known helium gas fields, which together with Labarge, discovered subsequently in the cliffside, which was a strategic US storage site, provided almost 90% of the West's helium until the 1960s, 1970s, until which others came online. The others that came online, Qatar and Algeria. This is helium supply today. That's the US, and you can see that US still dominates the helium production. Qatar and Algeria are huge producers. Small amounts from this is now gone. This is the strategic reserve that has now been sold off. Russia was due to come online. That was due to take 35% of the global market. Very briefly, helium prices stabilized. You can imagine this is an old slide. The absence of this coming online has seen the helium prices scream skywards again with a new shortage of helium supply. For helium and hydrogen, it's the same checklist. This is a helium exploration checklist, but as I've said, it matches hydrogen. We need, for any source, whether it's petroleums, this is the petroleum system, this is the helium system, but it's also the hydrogen system. We need a source rock. We know what that is. It's the broader continental crust. And it's uranium thorium decay and iron-rich rock, which cohabit. We need maturation for hydrogen and helium simply time. We need a mechanism to migrate those gases out to the near surface, mostly by diffusion, but there are regions where we're undergoing tectonism, where heat and pressure can accelerate that process. And once we've formed a gas phase, where and how do those gases migrate, and how good is the geological trap in which they sit? I've put in a couple of components here, but the principal one we have to think about is actually its capacity to retain highly diffusive gases on geological timescales. That has become more and more apparent. We can just look at the uranium thorium source rock, maturation rock for helium and hydrogen. I've already talked about it's the continental crust, and we also know that helium is generated in the same environment. Nitrogen is also generated. So we're looking at three gases, not just helium, not just hydrogen, but nitrogen is also often co-generated in these systems, and we know the ratios at which they're generated. We can walk in these source rocks. There are mines in Canada, in South Africa, which go down to 3.5 kilometers depth. This is a picture from one of those mines. This is Timmins. It's a volcanogenic massive sulfide deposit. Excuse the acronyms. They're mining it for they're mining this system down to now about 2,900 to 3,000 meters depth. It's a really cool place. I've only been to the surface. That's not me collecting samples down there. Because the Earth isn't exactly a sphere, it's a little bit oblate, it's squished at the ends. When you stand at the bottom of this particular mine, you are the closest you can be to the center of the Earth on the planet. Nothing to do with hydrogen exploration, but I think that's just a cool factoid. What's also a little bit surprising is that the rock isn't dry. The rock has a lot of water coming out of it, which is great because that means that water is reacting with the rock to generate hydrogen. It's reacting with the alpha particles, the beta particles to generate hydrogen. And no surprise, the gases coming out with the water are rich in hydrogen, also contain methane, and they're rich in helium, and they're rich in nitrogen. Some of these gases can be 60, 70, 80% by volume hydrogen. They can be up to 10. We've got one system which is 30% by volume helium. To be commercially viable, you need 0.3%. Flow rates don't work out, but this is the source rock for hydrogen and helium. We can walk around amongst it, and we can understand and characterize how it behaves. And we can show that some of these portions of the crust hang on to their gases. This hydrogen and helium isn't generated and lost. It sits down there and slowly migrates to the surface. The water in the water coming out of these rocks has possibly been down there for billions of years. But it does come out. It comes out either in steady state, that is, eventually the continental crust, if you like, fills up with enough hydrogen and enough helium that the amount produced is the same amount lost, and we see that fluxing at the surface. We can measure that in the helium, and we know hydrogen is related, so we know they behave the same way. But we also know the continental crust isn't always just sitting there passively. Quite often the continental crust undergoes events which builds mountains, or events which stretch and cause subsidence. Continents rift, and they collide. Sometimes we have hot spots, mantle hot plumes rising up from the Earth's core and providing point sources of heat, which is the reason we have volcanism in Yellowstone. Wonderful place to be, wonderful geysers. If you could put a plastic bag over Yellowstone and sit there for enough time, you probably have to sit around for quite a while, but if you sat around for 1 million years, you wouldn't. The amount of helium released would be 13 billion cubic feet. Excuse the cubic feet. That's enough helium to supply all of society's needs for about 3 years, 4 years. That's 24 to $30 billion worth of helium coming out of Yellowstone, and that's just the caldera. So this volcanic plume has heated up the crust. That continental crust, which is full of nascent fluids, has had them released by heating, by tectonism. I've got a plot here. It's not the best plot, but think of the y-axis as a proxy for temperature and the x-axis as a proxy for, well, I've got helium flux here, but it would equally be hydrogen flux. The average continental crust, which is not being heated by a volcanic plume or undergoing rifting, would sit somewhere around here. These are log scales. So we know exactly what the ambient passive continental crust looks like. We know what it looks like when it's on steroids, and we know what it looks like when there's really, when something like this has gone through and it's recovering. And we can calibrate that locally. We do understand that, and we can measure it. With that gas released, we understand as it comes to the surface, what are the processes that might capture it? What are the processes that might allow it to accumulate and form in a way which allows us to access it? This is the Hugoton Panhandle gas field. It's predominantly a methane field, but it contains, did I write this down somewhere? It's certainly greater than 0.3%. In some portions, we're getting up to about 1.5% by volume helium. As I said earlier, this is one of the principal sources of helium that supplied the West for the best part of 3/4 of a century. And what we can see is the role that the regional groundwater system has played in effectively forming a barrier over a wide region of the continental crust. And the helium has slowly come up into the groundwater system, accumulated in the groundwater system. And in this particular case, hydrocarbons have been generated by heating and pressurizing rocks containing organic matter, generates methane. The methane comes up, and the methane timing coincided with this groundwater system also containing, having sat there for long enough, containing a large amount of helium. So that methane creates a free gas phase. The helium that's sat in the water in solution, because it's insoluble, migrates into the gas phase. The gas phase accumulates at a structural high in the same way that oil and gas forms. It migrates up dip until it's trapped. forming one of the largest gas fields for helium in the world. It's almost depleted now, so as a commercial resource, we have used this up. There's not very much left, but it gave us a really good insight into the role of the regional groundwater system and its importance in capturing slowly diffusing gases out from depth. If you don't want to wait that long, go to places of the world where it's being accelerated, a little bit like Yellowstone, but think East African Rift, the African continent, which is ancient. The rocks are up to 2.7 billion years in age, so they've sat around for a long time, accumulating hydrogen, accumulating helium, and the entire continent is now trying to split apart. The continent is rifting. As it rifts, it thins, it heats up, there's volcanism, and that heating process drives out those gases which have accumulated in the continental crust for billions of years. And this isn't a very good picture, but this is one of our collaborators. In fact, he's the founder of a helium exploration company, and the gas bubbling out of that pool is about 10% by volume pure helium, not hydrogen. I'll come to that. But we've now got two companies who've floated on the public market. I say we. I have no part of those companies. There are two companies exploring for helium in this particular setting, and one of these, they're not discoveries, they are estimates that have yet to be validated. One of the estimates, if validated, would supply the world's helium for about 14 years. And that's just one of the discoveries. So I want to talk about helium as it comes to the surface. I've mentioned the importance of water, but I've also loosely talked about the importance of the geological environment, the architecture, if you like, of the system into which the helium is migrating, the architecture into which the hydrogen is migrating. This is work by Annie Cheng, and is sat at the back there. This is considering the continental crust just sitting there in a quiescent environment, so no volcanoes, no continental rifting, sitting there, reaching steady state, with the helium and the nitrogen diffusing out at the rate at which it's produced in the continental crust is the same rate at which it's inputting into. These are sedimentary structures. This is our first sedimentary structure, second sedimentary structure, third, and sedimentary basins build up over time with lots and lots of different layers. And critically, if your sedimentary basin is not particularly amenable to accumulating gas, helium will diffuse in and it will diffuse out again, and it will stay in solution. And this critical dotted line, which is the solubility limit, it's the bubble point, will never be exceeded. So we can generate a model which looks at how these basins accumulate over time. Let me see if I can get this running. Here we go. What we have is me messing up. Let's try again. What we have is the nitrogen concentration in the water, the helium concentration in the water, this critical bubble point simply not being reached for 250 million years, hundreds of millions of years. And at some point, when we've built up many sedimentary layers, in the deepest sedimentary layer, we hit this critical threshold where the bubble point is reached and critically a gas phase is formed. This is an entirely new concept for gas field formation. generated by the steady state diffusive release of gas from the deep crust over tens and hundreds of millions of years. This is completely different to the way in which hydrocarbon systems form and hydrocarbon systems develop. This gas, we know in many environments, is hydrogen-rich, is helium-rich, and nitrogen-rich. And with these types of models, and remember, this is a simple one-dimensional model looking at one point in one basin, so I don't want to place too much emphasis on the numbers that we're using here, but we're developing the capability to quantify the systems. We've got work to do yet, but with that model, in that particular run, we can quantify the amount of gas that is formed. We can place that against the amount of gas which is diffusively moved through the system. And we can identify, therefore, the amount of resource, in this case of helium, but equally so with hydrogen. And again, I don't want to place any great weight on the number, but it's always fun to play with these. If you've got 6% of your gas underneath that entire basin being trapped as a gas phase and as accessible, it's valuable. We know that what the surface area of the sedimentary basin is. We know what proportion of the continental crust it is by area. We know that over 1 billion years, we've got 170,000 present day oil production, another new unit. If 6% of that is there, we've got, I'm not even going to say the number, we've got an awful lot of hydrogen potential, and still only a small amount of that has to be accessible to be commercially valuable and contribute to a net zero society. But you wouldn't go to the Williston Basin to hunt for hydrogen because the rocks aren't particularly good. The rocks in the Williston Basin still allow helium to diffuse through, hydrogen to diffuse through with rapidity. What you really want is salt. Something very much like it, an evaporite. There's a particular type of tight rock where hydrogen and helium simply do not diffuse through. And this is in the southwest US. This is the Four Corners region between Colorado, New Mexico, Utah, and Arizona. A big basin called the Paradox Basin, covered with a salt layer many hundreds of millions of years ago. That salt layer is deformed by geological processes, but it forms a barrier to gases coming up from below. And we can show what that the effect of that barrier. This is work by Ballentine. It's just been accepted. We can show that we can look at the helium above the system. We can look at helium below the system. We can generate these models that Annie Shane has worked on and show that there is no diffusion through the paradox evaporites. This is a tight reservoir, a tight rock formation that does not allow hydrogen to escape. We can go to other parts of the world where there are big, wide salt deposits covering the systems regionally. This is the Amadeus Basin in Australia, just an example. Again, a widely occurring salt deposit deep in the sedimentary sequence. It will stop hydrogen and helium escaping. There have been a few wells drilled into the base of that. These are the gas fields identified. Two of them, McGee number 1, wonderful, it's full of helium, no hydrogen. Lots of methane though. Mount Kitty, similar amount of helium, but a large amount of hydrogen. Less methane. So what's going on? Why is it that systems, gas fields, not so far apart from the similar geological environment? One preserves hydrogen, one doesn't. So it's not simply trapping it that matters. It is preserving it chemically or biologically. And I just want to show some work that Rita Carolite has done, looking at the preservation mechanisms. So if we look at hydrogen in South African and Canadian fluids, we see in the deep mines, as I've already said, we find native hydrogen. It sits down there, it accumulates. The yellow here is the hydrogen you can see across the Canadian Shield, South African mines. A large amount of these fluids are hydrogen rich. And it's worth noting that the microbial activity in these systems is very low. They exist. There are sulfate reducers, there are methanogens, but the cell count rates are very, very low. So the activity of the biology in this hydrogen-rich environment is low. But when these gases leak to the surface, the hydrogen's gone. This is again, Witwatersrand Basin. That's not a very good figure there to show you where in the world it is, but this is South Africa. A lot of boreholes. These are the locations of surface boreholes where there's a large amount of gas coming out. It's helium rich, it's nitrogen rich. No hydrogen, but it's got methane in it. And this is some very nice modeling, simply taking our understanding of the porosity environment in which helium and hydrogen is produced, and understanding the quantitative, if there's quantitative conversion of the hydrogen to methane by biological activity, we can model what it would look like and how that would explain or otherwise the chemical constituents of the gases coming to the surface. And this modeling is completely consistent with both the radiolytic source generating the hydrogen, which is being converted to methane, but most importantly, all of that methane being derived from hydrogen conversion by biological activity to methane. So we've lost the hydrogen that was generated. It was generated at the proportions we expected, and then between where it was generated and the surface, it's been used up by the microbes. I'm just coming to the end of my talk because preservation and understanding the rate at which the microbial action takes place is going to be critical. This is work by Steph Flood. It's not quite submitted, we're almost there. This is looking at another one of these sedimentary basins, but this time in Brazil. We've got in these systems helium-rich gases, exotic stable isotopes, which show that the gases are not traditional hydrocarbons. These show that these are up to 40% by volume hydrogen, or at least they were. 7 years after drilling, the hydrogen hasn't completely gone like the South African example, but it's dropped by 50%. So with that South African example, we don't have a handle on how quickly it's happening, we just know it's happened. The Brazilian study is giving us indication that within 7 years, 50% of the hydrogen has been utilized, probably by microbial activity. The stable isotopes suggest that it's a microbial direction that the stable isotope system is all heading in. So I'm going to finish there. Really with one of the slides I used to start with. We've built a good understanding of how hydrogen is generated and is preserved in the deep crust. It is there. We've got an understanding of where it's released, and an understanding of what controls the rate of release. The processes and geology is complex. Every environment is different, but we understand the ingredients that make up a hydrogen prospect, and we understand the types of rock which will trap hydrogen on the timescales, which are very, very different because of the diffusivity of hydrogen. But I would say at the moment, the challenge that we have is to better understand the preservation of the hydrogen in the trapping structures. It's certainly getting there, but in many environments it's gone. in quite a few, we have the hydrogen there, but being able to predict that is where we need to be. And that is where I'll finish. Thank you.
Thank you very much indeed, Chris. Before we take a question, could you answer, is it pipeline or pipe dream? That is the title of the job.
I thought somebody would pin me down on that one. I think that it will almost certainly be locally significant and probably regionally significant. Whether it reaches the giddy heights of being globally significant, I think we've yet to understand it, because these are non-traditional areas that we're exploring and trying to understand. And in particular, the example of Mali is a little bit of a red, it's not a red herring, it's a very special environment where the hydrogen is pure, it's 95% pure hydrogen. Many of the systems I've been using as exemplars, you're looking at 50, 60, 70% hydrogen maximum, and the separation costs or the addition of methane are going to be additional cost elements which you have to fit into the economics of it.
Do we have some questions from the audience? Okay, just turn the camera on.
There's a question in the back there.
Yeah.
Okay.
Sorry. Oh. Just need to turn off the. Yeah. Well, no, I need to turn off the background effects. That's number one. So stop sharing around this end, and then we'll be with you. Sorry, Chris. I don't know if you can see. I'm trying to stop sharing down here.
What do I press?
The X.
The X, not the telephone call. Got it.
That's it.
Okay. In a second. Thank you very much. So please, yes, sorry.
It's really nice to see all the words that come together nicely. About staff's work. So I'm just quite interested in the rate of microbes turning hydrogen into methane. I'm expecting it's an exponential change, or is it more like a linear change? Or what is it? Oh, so.
Oh, that's a really good. That is a good question, and I think once you have microbial activity involved, it depends on whether or not they are seeing a new energy source and increasing their metabolism and growing as a response to that. So clearly, I mean, it looks like the system was microbially free until it was pierced by the drilling activity, and we suspect the oil company, we don't know, but we suspect the oil company injected fluids into it, which may have inoculated it with microbes. But if the microbes go through a doubling process, it may well be an exponential loss of the hydrogen, but we don't really know, so that's speculation.
So if I can just pick up on that point, should there be a protocol that says you should not be injecting things into some of these reservoirs in case it starts a microbial population growing in it and therefore affects the quality of the resource?
Totally, and it may also be relevant to thinking about geological hydrogen storage as well. You don't want to inoculate a nice a clean sandstone reservoir and then have your hydrogen. You know, if you're injecting hydrogen in and extracting it on an annual cycle, that's probably fine. But if you've got a microbial population in there eating 5% of it, that's going to cost you.
Can I just move to the online questions? I think the first person who had a question is Martin. Martin, do you want to try and turn on your camera, please? Sorry.
Yeah, that's great.
I'm just needs to enable that in a second. I might turn off this microphone just while we have the question. Okay, Martin, are you able to turn on your microphone or camera to ask your question, please?
Hello there, Chris. Can you hear me? Hello? Hi, sorry, can you hear me? Okay, I'm sorry.
Yeah, we can hear you fine, thank you.
That's great. I can hear you now. So I'm calling in from Austin, Texas. Good to see you again, Chris. So thanks for a great talk, Chris. I put some comments down just on the chat there about the interestingly in the Paradox Basin there is historic uranium exploration as well. And the Hugoton field, of course, is also adjacent to a very deep major fault along the bringing up the Wichita uplift there and possibly accessing Weissman. But I wondered if you had a general thought about the attractiveness of intracratonic basins in general, particularly if they have salt, as you mentioned. And one basin that came to my mind was the Michigan Basin, for example. And I wondered if you did anything there.
No, I did my time at the University of Michigan, but I didn't think to drill when I was there. I wasn't thinking of hydrogen and helium at the time. but yes, I don't recall where the salt layer is. I've got colleagues who were suddenly looking at the methane production related to some of the very saline fluids. But in general, if that salt layer is deep within the sedimentary sequence and widespread, it would be a very good place to look for helium and hydrogen accumulation. But obviously that's a very broad brush statement.
Yeah. But do you think intracratonic basins in general then are a good place to focus, or are you looking more at the basement itself?
No, I think the quiescent intracratonic basements are really interesting, particularly for helium exploration. They will have high prospectivity if they've got a salt layer in them. If they're good for helium, they will be good for hydrogen if we're preserving the hydrogen, and that remains our key limit in high grading those environments.
Thanks.
Okay, thanks very much for your question, Martin.
Yeah, sorry, thanks, Martin.
Lawrence, we'll come to you in just 1 second. The one question I want to ask from the room first was you talked about a 2030 time frame. So how quickly would we be able to prospect, develop and access the naturally occurring hydrogen at a volume that has an impact by 2030?
I can't speak to the volume that has an impact because that depends on the volumes down there. But assuming they are useful, there is no reason why we couldn't be producing within 5 to 10 years at scale, because the technology is mostly developed. It's in the hands of the hydrocarbon industry. It will be drilling into unconventional environments, but using conventional techniques.
Thank you. Lawrence, over to you. So just to interrupt you a second, Lawrence, your sound is coming through very strangely.
Oh dear, no,
Okay.
we can't hear you.
We can't hear you. So what we might say, could you type the question instead, because it's not intelligible.
Would that be better?
Oh, that's much better.
That's much better.
Okay.
Okay, fine. You don't need to see me anyway. Anyway, thank you for an excellent presentation. And learning about hydrogen and Earth's crust is quite amazing. What's interesting to me is the economics of it. You know, and obviously it's early days, and the geostats for finding hydrogen are again, it's early days. You know, I mean, finding oil in a sedimentary basin, we can do seismics and discover basins, and also you can do seismics today even for hard rock as well, which is also very interesting, as they do in South Africa. Drilling to the depth of a kilometer is about $7 million actually. And what I'm wondering here is that you're gonna have to punch a lot of holes to find hydrogen, and if you don't have the sort of exploratory skills that they have that are applicable to the oil industry. Finding hydrocarbon basins is a lot, in a way, today has become a lot easier, and it's no longer often hit or miss, right? Whereas with this hydrogen in the Earth's crust seeping through rocks that are where the structures, as you described, are not yet well understood or defined, it's going to be very challenging, I think.
Yeah, I agree, but in one sense, there's likely to be low-hanging fruit where that understanding can be developed in the same way that the hydrocarbon industry has grown and developed. So if when you've got systems which are tick all the boxes for being a high-grade hydrogen environment, where you've got source rocks, migration pathways, all of the work tells you that you would expect a free gas phase, and they're not too deep and inaccessible and therefore expensive. Those are the systems that you might want to look at first. And I don't think I think the technology that the oil companies have got with seismics would be more than capable of finding and high-grading those low-hanging fruit first. And from those, we can develop an understanding where the deeper, more expensive plays could be. But that would be the evolution of the industry if they turn out to be useful.
Thank you very much.
Thanks for your question, Lawrence. Do we have any other questions in the room? Okay, well, I think that my final question is, it sounds like it's a race between the microbes and the explorers to actually get to this hydrogen that's built up over maybe 1 billion years, and maybe those pesky microbes will beat us to it. I don't know if that's true.
I think identifying where the microbes haven't been or have been, where the environment has been sterilized, and getting down there without stimulating any more microbes will be a key part of any strategy.
Okay, well, thanks again, Chris, for your talk. That's been great.
Yeah, you're very welcome. Thank you.
Quick advert, next week, the final seminar of the year in the Oxford Energy Seminar Series. Excuse me for appearing on the screen in a scary manner to people in the room. And Ekaterina Bobrova from ECI and from the CREST project will be picking up on, I think it's quite a timely topic. It's about homeowner renovation to improve energy efficiency, but it's really essentially to understand motivation, what knowledge you need, and how closely involved you need to be to make that work effectively. Thanks again for joining us this evening, and thanks again for Chris for a very helpful guide to gold hydrogen. Have a good evening, everyone.
Thank you, Robin.